We will start this in a rather general note. We will say that suppose I have a physical quantity A. Okay, I have a physical quantity A, which can be anything, which can be temperature, momentum, velocity, mass, whatever. Some physical quantity which can be a vector, scalar, or tensor quantity. I'm not going to make it bold or anything. I'm just going to make the point that it can be anything. We are going to probably derive the equations for specific quantities. We can't derive it for all of them, but extension to any other form of physical quantity is most of the time trivial. So this can be a vector, scalar, or a tensor, and this is a whole quantity. So if we say A is mass, then its units are kilograms. If we say its momentum, its units are length times mass times velocity. So this corresponding to this quantity, we derive a quantity which will denote by this fancy A, which which can vary from point to point and which can vary with time as well. And this is known as a specific quantity corresponding to this quantity A. So this specific quantity is simply A per unit mass. In some books, in some cases, a specific quantity is derived as A per unit volume, but we will define it as A per unit mass. So whenever we have this fancy kind of A, it is a specific amount of A, so it is A per unit mass, and this is a function of both position and time. So if I want to take the total derivative of it, so if I want to take d dt of A, the fancy A, then I will have to take d time derivative dt dt plus space derivative this is the velocity at the point x, so this we call vk. So this is what we have, and this ddt we use this operator to describe total derivative with respect to time. We don't use this because we sometimes can confuse it with other things. So we use this capital ddt to denote the total derivative. So the total derivative of A now has two parts. Of course, dt dt is one. So it has two parts. One is this and the other is this. So these two parts are physically, you need to understand it physically. So finally, this term describes the rate of change of A with respect to time if you are standing at a point x, and this is sort of embodying the rate of creation or destruction of A at that point. Whereas if you take a snapshot of the body, then this term describes how A is being carried away from that point outwards along with its velocity at that point, how A is flowing out of the point in the direction of its velocity. So these two terms together make up the total derivative, and this total derivative equation can actually be written for any quantity. In this case, A can be any quantity, scalar, vector, or tensor, and when you write it for any of those quantities, this is how you write it as. You might have realized that this quantity is del x j of A, and this is the jth component of nabla. So this is the jth component of nabla. So this is the gradient. So I have the gradient here times the velocity. So this gives the vector form of the total derivative, and in place of this, in place of this wildcard, you can put any physical quantity, scalar or a component of a vector or a component of a tensor into it. So you must remember that if you put, for example, the component of a tensor here, if you put Tij for this wildcard, then here you will get Tij, and the gradient of Tij would then be a third order tensor, whereas if it's a scalar like here, then it would be just a first order tensor or a vector. Okay, so another way of looking at it is to look at what is known as the Reynolds transport theorem. You might have done this already in your fluid mechanics courses. We are not going to derive it, but the Reynolds transport theorem says pretty much the same thing, but from a different point of view. So we have said that A is per unit mass. A is A per mass. Okay, so if I have a small volume dV, the mass of that volume is rho times dV. Rho is the density at that point x. So I have a small volume around x, and then let me write it. Okay. So I am at a point x where the density is this. So the volume of that small element around x is dV. So this is the mass of the element. Then if I multiply it with A, then I get the total amount of the quantity A in this small volume dV. If I integrate it over volume omega, remember omega I have taken to be a sub-volume of V. So it can be any arbitrary sub-volume of V, then this is the total amount of A contained in that sub-volume. Total amount of A contained in the sub-volume. Write that down. Is omega, which is a sub-volume of V, is this quantity. And now I want to know what is the rate of change of that total quantity. What is the total rate of change? This is the total derivative, remember. And what is the total rate of change of this whole quantity contained in the volume omega? So what I'm asking is that inside omega, how is A changing, the total amount of A held by omega changing with time? Now Reynolds transport theorem gives me an answer to it, and the answer is it can be proved, of course, and it might have been proved in your fluid mechanics courses. Not going into the proof, but the answer is kind of obvious. It's this is what I have set out to find. This is the rate of change of the total amount of A held inside this volume omega. And Reynolds transport theorem says that it has two parts. One is this, and the other is this. So before I go into what these things mean, let us write this. So we have written the Reynolds transport theorem for the case where A is a vector quantity. Obviously, it can be written for a scalar or components of a tensor as well in exactly the same way. So in place of AI, I could have put Tij, or I could have put phi, which is a scalar. So the statement would remain the same. So convert this. So see that I is a free index. So I is everywhere, and you can I guess see that this, with j being the repeated index, is v dot n. So it is, this n is the outward normal to the surface, and v dot n is what this turns out to be, the surface integral. And this, when you write this equation in terms of vectors, you write it for a1, a2, a3 and put them all together, then this is what you get. So this is the Reynolds transport theorem in its vector form. Okay. Obviously, it can be written in the same way as for a tensor or a scalar as well. Now, uh, this again represents the amount of A that is being created or destroyed within the volume omega over time. This represents the amount of A that is leaving or entering the volume omega through its boundaries. So, in some sense, this says that the total change in the amount of A in omega is composed of two parts. One, which is how much total omega is being created or destroyed inside omega. So how much total A is being created or destroyed inside omega, and how much of it is entering or leaving through the boundary. So that's the boundary integral, and that is the volume integral. This is the creation or destruction integral, and this is the exit efflux or influx integral. Now, this is pretty much like what would happen when you put money in your bank. So, if I ask you the question that how much money, what is the rate at which money in your bank account is changing? So, it will have two parts. One, the bank is giving you some interest. So if even if you keep your money there and don't put any money in, uh, your money will grow because the bank is giving you an interest, and that is analogous to this term. So this is the growth of your money um, that is happening if you keep it inside your account. Then you are withdrawing money and depositing money all the time. So you get a salary, you deposit money, and then you withdraw money because you have to pay your mess bills. So you keep on depositing and withdrawing monies, and that is analogous to this term, that is the inflow and outflow of money. So at any point of time, your rate of change of the money that you have in your bank account is the rate at which the bank is giving you interest, plus the net rate at which you are depositing and withdrawing money into your account. So that's all. It's a Reynolds transport theorem is basically a bookkeeping statement. So now let us look at a straightforward application of the Reynolds transport theorem. Now, the most straightforward application of the Reynolds transport theorem is to write down the equations governing the balance of mass in a body. So we all know that the total mass contained in omega has to remain constant over time, which means that ddt of uh, rho dV is the mass contained in a small volume. That integrated over omega is the total mass contained in omega, and ddt of that has to be equal to 0. This is my equation of mass conservation. This is equation of mass conservation. And herein, remember, I am talking about mass. So A is mass per unit mass. So for the case of mass, A is just equal to 1, which if you put 1 here, this is what you will end up getting. So I can write the Reynolds transport theorem now with A reduced to 1. So this is reduced to 1, and this is also reduced to 1. So if I write the Reynolds transport theorem now, this is, so I write it in this form. So what I will write is ddt of rho dV is equal to So this is my balance of mass, and that's what I write here. So this is my balance of mass, Reynolds equation for balance of mass equal to 0, because inside omega mass is neither being no mass is net mass change is happening. However, mass can still be flowing inside the body. So that possibility is here. Mass can flow from one point to another point with the velocity, can flow with the velocity. And that possibility is in this term, but the total rate of change has to be equal to 0. Now, to this is a surface integral. I can convert it into the volume integral by applying the divergence theorem. So to apply the divergence theorem, I have to look at the index of n. The index of n is k. Therefore, and the function, the entire function has to be taken. So when I convert it into a volume integral, I get a integral over omega, and that will have del x k yk, because nk had k in it. So it will have del x k of rho vk, and this both are volume integrals. So this is going to be dv. So this has to be a small v. I'm sorry, this has to be a small v. So I take the volume integrals together. Del rho del t plus del x k of rho vk is equal to integral dv is equal to 0 over the whole omega. Now comes an important argument. The important argument is that, look, I suggest that no matter how small this arbitrary volume omega be, this statement must always be valid. So I can shrink omega down to the level of dv, and then still this equation has to hold. That is the essence of continuum mechanics. So this has to hold for no matter how small omega is. And in that situation, the only way that this can happen is if this term inside the brackets, if this term inside the square brackets is 0 for any dv possible. So this is known as the localization argument, and the localization argument tells me that for this to be valid, for any arbitrarily small omega volume, I must have del rho del t plus del x k of rho vk equal to 0. This is the law governing balance of mass. This is called the local balance of mass or continuity equation. Okay, what about this? This is also a balance of mass. This is just for a domain omega, a larger domain omega, which may not be infinitesimally small. This is a point-by-point relation. For every point in the body, this relation must be satisfied. This is a local form of the law of balance of mass, whereas this is a global form because it is integrated over a possibly non-infinitesimal volume. Both of these are balance laws, but this is, you will imagine, a more forgiving form of balance law. I'll tell you why. But this is called the weak form of the balance law. This is the weak form of the continuity equation or the mass balance law, because this allows you to satisfy mass balance over an extended volume. So there is no compulsion on this to have this quantity be 0 at each and every point. It can be positive at some point, negative at some point, cancel out. All you want is, in a weak sense, over the whole volume omega, it should be equal to 0. So you are asking less from this equation than you are asking from this. This is known as a strong form. This is the strong form or local form, which has to be valid at each and every point. It is much less forgiving, whereas the weak form is much more forgiving than this. Both obviously say the same thing, that mass can neither be created nor be destroyed. So we will deal with weak form as well as the strong form in this course. However, to go from the weak form to the strong form like we have done, we need to apply this localization argument that I just applied. The localization argument is that the weak form should be valid no matter how small this volume omega is. If that is the case, then this integrand has to be zero at each and every volume. It has to be zero at each and every volume, and this statement leads to my strong form. So unless I can make this assertion that the weak form has to be valid for each and every volume in the body, no matter how small, I cannot apply the localization argument. And in this course, I will apply the localization argument left, right, and center, uh, which will, which in some sense, in some sense embodies the fact that I'm dealing with quantities that are smoothly varying over the whole domain. There are no surprises in the variation of, say, rho over the volume, of density over the volume. There are no regions which have rho going to very high values close to infinity or so on. So there are no such regions, so that no matter, and also the discreteness of matter is completely ignored. The matter is not discrete at any point. It is completely continuous, and the localization argument, the validity of the localization argument essentially encompasses the fact that I am dealing with a continuum with a slowly, decently varying varying variables. All quantities on the volume are varying in a slow and decent fashion. There are no surprises, as I said. There are no singularities. There are no points where it goes to infinity and so on. So there are no points where the, say, density is multiple valued and so on. So if all these things at the background are satisfied, then the weak form goes to the strong form quite seamlessly by applying the localization argument, otherwise not. Having said that, I will be applying the localization argument, but it is important for you to remember that behind the localization argument are a lot of assumptions that can break down in very, very special and but important cases in mechanics. Okay, so this is the strong form of the conservation of mass. So this is the strong form of the conservation of mass in vector form. So remember, we had del, if we go back, so this is what we had. We had del rho del t plus del xk rho vk equal to 0, and this you can probably map now. By now you can map to this term here. So this is your strong form of continuity equation. Okay, so now I will look at linear momentum, and let us see what linear momentum is. So momentum is mass times velocity. Momentum per unit mass, so this is my A, this is the total quantity, and the specific quantity would be momentum per unit mass, which would just be V, right? So velocity is the specific momentum. Velocity is the specific momentum. It's a vector, so we'll see how it behaves according to, in the light of what we have done.